Okay, so this is for our exam question that says a 10 centimeter long uniform cross-section capillary initially contains pure water on the left and D2 on the right. At T equals 0.1 seconds, the maximum molar diffusion is 2.78 moles per meter squared seconds. So our first question is asking what the overall mass flux corresponding to the maximum molar diffuse flux is. So in this situation, we can start by thinking about our molar flux. So our net molar flux is going to be 0 because for every 1 mole of water that's moving to the right, 1 mole of D2O is moving to the left. So if we're looking at a component molar flux, this bulk contribution is 0 because this total molar flux is equal to 0. So now when looking at the mass flux, we can't assume that our net mass flux is 0. So we have to calculate it to see what the individual mass fluxes are and add them together. So the mass flux for one component, so let's start with water, is equal to the density or the mass concentration of water times the velocity, and it's also equal to this side of the equation because we don't have our total mass flux and we don't know our mass diffusivity flux, we'll use this version. So from this, we don't know our velocity, but that's something that we can find using our molar flux equation. So with our molar flux equation, our velocity of water is equal to the molar diffusivity flux divided by the molar concentration. So now we can plug that in to our mass flux for the individual component, and we get that it is the molar diffusivity flux times the molecular weight. So when we calculate that for the mass flux of water, we get 0.05 kilograms per meter squared, and then for our mass flux of D2O, we use negative 2.78 because the flux is in the opposite direction. So we get negative 0.0556 as the mass diffusivity flux for D2O. So to get the net flux, again, we add those two together and we get a total flux, mass flux of negative 0.00556. Even though this value is pretty small, we can't assume it's 0 because the densities are different in this situation. Okay, so for number 2, to make an order of magnitude estimate for the maximum driving force of diffusion at t equals 0.1 seconds, first I looked at what is happening at the initial state. So at t equals 0.1 seconds, so right when our system, we're looking at it starts, I guess, we have non-steady state diffusion. So what that means is our concentration is changing with time at a specific position. Also, it's important to note that our total concentration, though, is constant. So since we're looking at driving force at a constant temperature, so looking at driving force at a snapshot in time, we can see how it's changing with position. So I started with the Fick's equation for binary ideal solution. So we can isolate the driving force, and we're looking at the magnitude of it. So we have that it's equal to the molar diffusive flux over the total concentration times our diffusivity coefficient. So that's 2.78 moles over a meter squared per second times our total concentration here, which is 55.5 times 10 to the third moles over meter cubed times our diffusivity coefficient for liquids, which is 1 times 10 to the negative 9 meters squared over second. So that gives us a magnitude estimate for maximum driving force of diffusion as 5 times 10 to the fourth. Okay, so for part 3, it's asking to sketch the initial at t equals 0.1 seconds, at t equals 60, and at some time infinity seconds, um, and see the mass transport profiles at those 3 points. So the first set of graphs are looking at the mass concentration. So the density of pure substances is equal to its mass concentration. So in this case, both our H2O and D2O are pure. So from 0 to 5, from this part of the tube, we have that the mass concentration is all water, except for a small portion near 5 centimeters where some diffusion has occurred because we have a molar diffusive flux of 2.78 from previous parts. So that's why we have at 5 the concentration changing here. Again, when we go to the right, it's mainly all D2O until we get really close to our 5 centimeter interface portion. At the intermediate time point, we have that this diffusion is more completed. So we have a portion of the concentration on the left due to water, and but also has some portion of D2O. And then finally, we have the system reaching steady state. So our mass concentrations of the individual components are constant, but they are equivalent to their densities, so they are not exactly the same. Molar concentrations, this follows a similar trend. The tube from 0 to 5 centimeters is primarily the moles of water, and then from 5 to 10, it's primarily the moles of D2O. And then at 5 centimeters, again, we have the diffusion starting. So there's some components of D2O just to the left of 5 centimeters, and some components of water just to the right of 5 centimeters. And then at some intermediate point, we have the mixing occurring. So there is, even though the individual molar concentrations add up to be the same net value, there is more water on the left and more D2 on the right, but some components of each in the other sections. And then finally, when you reach steady state, we have that both those molar concentrations are at equilibrium. They are constant throughout the entire tube. For our molar diffusivity fluxes, we are given the value of 2.78 at t equals 0.1 seconds. So right when our system begins, per se, our maximum flux is at 2.78, so right at 5 centimeters, because that's where the moles of the two molecules are interacting. Then at some 0 to just before 5 and from little after 5 to 10, we see that those molecules aren't seeing other or different molecules, so they don't see diffusion. They don't have a driving force for diffusion yet. As we get to some intermediate time point, we have that at 5 centimeters, you don't have your maximum diffusion, but that is the location where the most of the diffusion is happening. And as we go to um, the ends of the tube, that is less prominent because again, there's less moles of each of those components on either side. And then finally, this portion here, we've reached steady state once again. So um, there is no flux. So that's why there is no molar flux. So both our components um, are at 0, molar diffusivity flux. And then here for our total mass flux. So from our first problem, we saw that our net mass flux is equal to negative 0.0056. So that's why at 5 we have that peak, and then to the rightmost and leftmost sides of the tube, those molecules again don't see other components, so they don't see that same diffusion. And that peak slowly broadens out at some intermediate point because some of our molecules on the left and right have mixed, so that driving force isn't as great. So our mass flux here is less. And then at a final time point where diffusion is, there isn't a concentration gradient for diffusion, our mass flux is zero throughout our system.